We're going to continue. We did the electromagnetic spectrum last time, and we're now going to have a look at electrostatics. Okay, so we're going to have a look at basically changing, because they do ask you sometimes the following to the units shown. Okay, nanocoulombs to coulombs, blah de blah de blah. Right? What do we do with these? Okay, well, the first thing about it is to say to yourself, right, 150, let's look at question 6a, all right? 150 nanocoulombs, okay? What does that mean? That is 150 times 10 to the minus 9 coulombs, all right? So what do they actually want? They want it in coulombs, right? Now you're going to write it as 1.5. Okay, so we've moved the decimal place, so it's going to be 1.5, okay, times 10 to the minus 7 coulombs, right? Because we've moved the decimal place. B, 0.5 coulombs, okay, 2 millicoulombs, 0.5 coulombs. So where do we want to be? This is coulombs. We want to go down to millicoulombs, don't we? So if we're going from coulombs down to milli, what do we have to do? We are going down, so we're going to times, and we're going down 3 steps. So times by 1,000, okay? So 0.5 times 1,000, okay, is going to be equal to, well, 1, 2, well, let's just do it. 0.5, okay, and we're going to times it by 1,000. 1, 2, 3. Okay, is going to be 500 millicoulombs, isn't it? Okay, 500 millicoulombs. Okay, let's have a look at C. Okay, C is 60 millicoulombs. All right. Okay, let's have a look here. All right. Yep, 60 millicoulombs is 60 times 10 to the minus 3 coulombs, isn't it? Right? Now, where do they want us to be? So we just have a look. They want us to be nanocoulombs. Okay, so there we're at coulombs, aren't we? Now we want to get down to minus 9. So we've got to go down from coulombs, right? Coulombs down to milli is 1,000. Micro is times another 1,000, isn't it? Okay, and down to nano is times by another 1,000. So we're taking it, can you see, I just went to coulombs first. Milli is 10 to the minus 3 coulombs. So therefore we're going to say it's 60 times 10 to the minus 3 coulombs multiplied by 1,000 by 1,000 times 1,000, okay? And if we do that, let's just do it together. 60 times 10 to the minus 3, okay, is that 3 over 50, you should be shown, times 1,000 times 1,000 times 1,000, 1,000 is equal to, and this is what it gives me, 6, 1, 2, 3, let me just count, 1, 2, 3, 4, 5, 6, 7 zeros, right? Which means if I put that into scientific, it becomes 6 times 10 to the 7 nanocoulombs, okay? And therefore, we're going to have the next one is 0.05 nanocoulombs. D is 0.05 nanocoulombs. That is 0.05 times 10 to the minus 9 coulombs. Now where are we going to move it to? Microcoulombs, right? So coulombs, we're going to go down to millicoulombs and down to microcoulombs. So we're going down over there and we've got to times by 1,000 and times by another 1,000. So it's going to be 0.05 times 10 to the minus 9 multiplied by 1,000 multiplied by 1,000, and essentially that is going to give us, let's look, 0.05, oops, not 0.02, 0.05 times 10 to the minus 9 equals times 1,000 times 1,000 is going to be equal to, whoops, and it's 5 times 10 to the minus 5. Okay, microcoulombs. All right, got that? Cool. Next, now let's have a look at this next bit. Okay, the next piece is where we're going to actually start doing some work. Question 8 is, an ion has a charge of that. Okay, how many electrons have been removed or added, and explain? Okay, here you can see where the physics and the chemistry are starting to overlap. What are we talking about? We are talking about, let us take for example, that we have, here's the nucleus, remember, protons and neutrons and protons, and we had electrons floating around, correct? This is question number 8, right? Question 8. We've got electrons floating around, all right? Now they say, how do we form an ion? Well, we remove electrons or we add electrons, right? If I remove an electron, what do I get? I create a positive ion, don't I? If I add electrons, okay, we create a negative ion, right? Because there's more negatives than positive. And what is the fundamental charge, electric charge? It's the charge on one electron, isn't it? Okay. Everything is in multiples of one electron. And the charge on one electron is minus 1.6 times 10 to the minus 19 coulombs, right? So all our charges that we deal with are built up solely out of electrons, taking them away one by one or adding them one by one, okay? Quite a laborious process, is it not? Right, so what we're doing is we're taking this little guy and we're adding or subtracting them from an atom, okay? Right, so what do we do? So, okay, an ion has got a charge of minus 6.4. So here's our ion, okay? And the charge on this guy, and we say charge is what? Okay, Q is equal to N times E. The charge in coulombs is number of electrons times the charge on one electron, isn't it? Why? Because each time, if I add one electron, let's just have a look at a table here, okay? Because sometimes this people get confused. Let's say electrons. One electron and then charge is going to be 1.6 times 10 to the minus 19 coulombs. If I now put 2 electrons on there, I get minus that plus another one, minus 3.2 times 10 to the minus 19 coulombs, correct? If I add another electron onto that, let's say 3 electrons, okay? What is my charge going to be equal to? It's going to be 1.6 times 3 is going to be 4.8. Right? If we add 4 electrons, can you see the charge is number of electrons times 1.6 times 10 to the minus 19. Okay? So if I know that my charge on the ion is, let me see, minus 6.4, that's Q, times 10 to the minus 19, is equal to N times minus 1.6 times 10 to the minus 19. So therefore, number of electrons is going to be minus 6.4 times 10 to the minus 19 over minus 1.6 times 10 to the minus 19, and I think that is going to be equal to 4. 6.4 divide 1.6 equals 4. Okay, so therefore if we've created this, we have That's plus. We've added 4 electrons, okay? If they'd have said the charge is positive, okay, N would have been a plus over a minus, wouldn't it? Would have been plus 6.4 over minus. It gives us a minus, which means we removed 4 electrons, okay? But just logic it out if you're unsure of the plus and the minuses, right? We have added 4 because we've made it more negative, okay? A charge, okay, whoops, just put this all back to black. Next page. A charge of 3 picocoulombs. Whoa, this is question 8b. Okay, a charge of 3 pc. That's a new one, isn't it? Okay, how many electrons have passed through? So this is the charge that flows. This is Q, isn't it? Right? Okay, now, if that is Q, right, what does pico mean? Remember, okay, what we did before is we said millicoulombs is 10 to the minus 3. Micro, 10 to the minus 6. Nano, sorry, I was just thinking there of pico. Nano, please go there. There we go. Nano is 10 to the minus 9. Okay. Picocoulombs, 10 to the minus 10, 11, 12. Okay. Okay. All right. So we've got that now. Okay. So let's have a look. We know Q and we know E is equal to minus 1.6 times 10 to the minus 19 coulombs. So they want to know how many electrons was this, all right? Well, let's see. We know Q is equal to N times E. So Q is 3 times 10 to the minus 12 coulombs. Must be equal to N times 1.6 minus 1.6 times 10 to the minus 19. So therefore N is going to be 3 times 10 to the minus 12 over minus 1.6 times 10 to the minus 19. All right. And if you do that whole lot, you come to minus 1.875 times 10 to the 7 electrons. Okay. Very small charge, but a lot of electrons. Okay. That's like 18 odd million of them, isn't it? Okay. So it's a lot of electrons that are flowing through at that time. Okay. Let's now have a look at the next problem. The next problem, let's go back to the problems themselves. All right. They say over here, all right. This is question number 9, all right. 2 objects are charged, etc., etc. Let's have a look at question number 9. Question number 9. 2 objects charged as shown are suspended on an insulated cord. Explain what is meant by insulated cords and why we need to use them. Well, first of all, we got to then say, what is insulation? Okay. If something is insulated, you know that, for example, if you look at an electric wire, there's a piece of plastic surrounding the wire, right? Why is it not just a piece of copper? Well, simple. If you touched it, what's going to happen? You are going to become part of that flow of electrons and you're going to change your hairstyle rapidly, okay? Including probably your heart rate and probably fatally too. So the question here is the insulation of the plastic protects us from the flow of electric current, right? So the insulator means it does not carry a charge. Okay? It doesn't carry the charge. So what's happening is the electrons are flowing. There's my copper wire. The electrons are all flowing down there, but the plastic around it, no charge flowing in that, right? So it doesn't carry a charge. So it is insulated means what? It means this, that there's the ceiling, and here's this thing, and this has got a charge on it. Doesn't matter what you want to call that charge. What's going to happen if this thing and that thing are in contact? The charge that's on here is all going to go up and away. It's going to go and it's going to discharge. In other words, the charge leaks away. Okay? It's going to go up to the ceiling. Why? Because it goes to earth or to ground. Okay? That is why in electricity we earth something. Okay? That is why when you've got lightning around, you've got the lightning rods, it goes to the earth. All the charge gets taken down into the ground. Okay? So therefore, that is what we're going to do. We say that is our, an insulator will not allow charge to move from one place to another, doesn't permit the flow of electrons, hence an electric current cannot flow. We use it so that the charges on A and B remain, or else they would leak away. Okay, that's what I answered. Okay, question B. Okay, question B over here is, using the diagram, show the electric fields and indicate if it's attraction or repulsion. Right, so now we have got this. And there's my ceiling, or whatever it is. And I'm going to label them exactly as per the diagram. A, B, 10 millicoulombs and 24 millicoulombs. Plus 10 millicoulombs minus 24 millicoulombs. Okay? Now I know there's a little formula that everybody uses, but just look at it from a point of view of, never mind the formula, let's just look at what this means, right? You remember, like charges repel. Same as magnetic, right? North and a north pole. They push away. They don't want to be together, do they? I had my magnets around here, they've moved off. But like charges also repel. A negative and a negative don't want to be together, and a positive don't want to be together. But here we've got similar charges attract. North pole and a south pole. What happens? The north pole says come here and the south pole says come here. So they move together. You've obviously done that many times with the magnets. You put it there and it attracts the opposite pole, correct? So what have we got here? We've got a plus and a minus. So we are going to get a force of attraction, right? And what do we always do? We always show the force, the lines of the field. Magnetic field go from north to south. Electric field from plus to minus. So we say, right, you are going to be plus and you are minus. Therefore, I draw a field that way. Right? And we know they don't cross. There's my little arrowheads. Okay, I'm not an artist. Okay, there's the little arrowheads. That's what she's going to look like, isn't it? Okay, so there's a force of attraction between these two, and we always draw the arrowheads from plus to minus. Therefore, if they ever gave you something and said, okay, guys, what happens here? This is, let me not use A and B. Let's just use a hypothetical X and a Y. And they show us this. And they ask us, what are the charges on X and Y? You always say, well, the charge here must be plus because the arrow is going away. The charge over here must be plus because it's going away, which means it's a repulsive force between two positives, right? If it was an X and a Y, like that, and we had, let's say we had this coming in like so, right? It means this must be a minus and this a minus because the arrows point towards the minus. And it's a repulsion again, isn't it? Okay? So just watch out for that. Magnetism, they often give it to you as well. Identify which is the correct field. Okay, I'm just going to wipe this out because I don't really want them. All right, I suppose I could have left them, but what the heck. Now, the next section is we're going to have to work with the charges that are on here and look what's going to happen as we, well, let's read. What do we do? Okay, what do we do? Show the electric fields, indicate traction. Okay, the two objects are touched and then separated. Using a diagram, show the electric field and and after that, show the charge and show how many electrons are transferred. Okay, this is a standard question, isn't it? Okay, after, of course, they've asked you what is the law of conservation of charge. Okay, charge cannot be, you know the rest of it, right? Okay, so what have we got here? We've got A and B. Oops, this is my A, and this is B. This is plus 10 millicoulombs. This is minus 24 millicoulombs. Now we come along and we push these together, A and B. We're going to have to put a force to do that, right? Because, well, not in this case, they're attracting each other, so there is a force. So what do? This one has got plus 10 minus 24. I've just left off the millicoulombs just for the moment, okay? Please bear with me, right? What do? I say, okay. In this situation here, I say, okay, we've pushed them together. So what have we got here? Let's say we've got, never mind the milli, as long as they're both the same, all right? What have we got? We've got a plus 10 and a minus 24. So what happens? Let us just say we've got 10 pluses here. Okay, so we've got 10 pluses. This side we've got 24 electrons, right? So what happens is that all of these electrons go back home, don't they? Okay, so 10 electrons flow that way, don't they? So 10 electrons go across there, which cancel out those 10 positives. Because if you've got 10 plus 10 minuses, you end up with 0. So 10 electrons go and cancel out 10 positives, 10 protons. Okay. What are we left with? We are left with, let's just go to red. We are left with what? Well, 10 have gone. We're left with 12 electrons. Okay, times, right, 10 to the minus 3 millicoulombs, correct? We can now put that back, right? With me? So what have happened is we just looked at it as electrons, but the coulombs, that charge, is a measure of electrons. It's the same thing, isn't it? You could go and work out how many electrons, there'll be a lot, but you could work it out. But all we've said is that I've got a charge of 10 there and minus there. So what am I going to do? I'm going to average it out because 10 of these are going to go across and get rid of 10 positives. So we're left with 12 minus because it's negative charge. What happens to those charges? Where do they go? You know that the charges, okay, there's A and B. What do? They go and they spread out. Whoops, sorry, I'm using plus signs. Shouldn't do that. Okay. They go and they spread out as far as possible. Why? Because they're negatives. So they try and get as far away from each other as they can. So they go to the sides. They spread out as far as they can from each other. And they sit on the surface, right? Because that's the furthest they can be away from each other. Then what happens is we move them away from each other. All right? So what are we left with now? Okay? We are left with, when we move them away, on A and on B. Okay? This was a total here of minus 12 times 10 to the minus 3 coulombs or millicoulombs. What am I left with on this? Minus 6 millicoulombs, minus 6 millicoulombs. They split up equally, right? That's what we're left with. So we're left with two of these, both with negative charges. What happens then? Well, quite simple. We end up with the negatives, so we have to draw our arrows coming in like that. correct? And we bring one in this side. And this is the arrow showing it's coming from a positive now to a negative, and it is repulsion. So they want to push away from each other, okay? So therefore, what have we got? Did I do that right? 10, 14. Oh, sorry, my bad. My arithmetic. Oh, terrible. Sorry. It's 14, so it's 7. Ooh, that was terrible. Okay. That was minus 7 millicoulombs. I'm glad I picked that one up. Let me just go back up here. 10, 14 leaves us with minus 14. Okay. All right. Minus 14. Sorry. But essentially, that's what's happening. Just go through the logic again. You've got the 2 sitting here. Even if they say 20 and 10, you put them together, they even out of a plus 30, which then makes it plus 15 on each. Then it becomes from repulsion to repulsion again. Okay? So how do we do it? You look at them and you first of all say, right, it's positive, negative, it's repulsion or attraction. Draw the line always from positive to negative, right? Then just look at it and say, if you touch them together, what's going to happen? Essentially, the negatives are going to flow from the negative one to the positive one. So how many we had in this case? 10 times 10 to the minus 3 coulombs flowed, didn't it? Right? 10 millicoulombs. Not millicoulomb, coulomb. 10 millicoulombs flowed, correct? I hate it when it does that. 10 millicoulombs flowed, here it is, from B to C. Because your electrons went from your negative to your positive, didn't they? So 10 millicoulombs went from B to A. B to A in this case. B to A. You silly sausage. B to A. Right? How many electrons is that? Well, Q is equal to N times 1.6. Okay? And we had that flow. It's a negative, all right? It's a negative, or we took it away. It's not really too critical. Okay? Flowed from there to there. N times 1.6 times 10 to the minus 19. Okay? So how many electrons went across? Let's have a look. 10 times 10, on 10 to the minus 3 equals that. 10 to the minus 3 equals that. Divided by 1.6 e to the minus 19 is going to be 6.25 times 10 to the 16. Okay, electrons flowed that way. All right. So that's what we're getting. All right. Remember, they're not difficult. All you do is you look at which way it's flowing. Your negatives got your electrons flow from there to the positive, don't they? Right. Up at my time, we've got to the end of question 9. Okay, and I've basically got it. Yep. There we go. So now next we're going to carry on, and we're going to do, from the next one will be question 10. Okay, then we're going to look at some of those tables and electric circuits as well. Okay, right. Thank you for watching this. Please just think about all you're doing in this, guys. I know I'm repeating myself. Please, I do it. All you're doing is you're taking electrons and moving them, right? This is the static electricity that you feel when you walk around charged up and you put your finger on, especially in winter. Okay, I'm not going to do the whole thing. Winter is coming, but you know what I mean is then it becomes, you walk across a carpet, especially I think nylon carpets in offices very often. Possibly the wool is just as bad, but if it's not been treated or earthed, you pick up a charge, and at night you can see that bright flash as you touch the handle, and it's pretty darn sore because you're getting that little lightning bolt coming across to you. Okay, that's the end of that. I'll be back and we'll continue with a little bit of electrostatics, and we'll get into moving charges, which is electric current and electricity. Cheers. Have a good one. Bye.